is to basically complete the basic picture of FRW spacetimes, get the basic physics of them, and end with a basically brief encapsulation of the current standard model of cosmology, the so-called lambda CDM model, which, yeah, you saw. I don't know if you were at the talks yesterday, you saw Kendrick give a nice encapsulation of it from another standpoint. Okay. So basically, again, when I say understand the physics of FRW, we want to understand kinematics, how particles move through the space-time, basically how geodesics behave, and then dynamics, how matter responds to the expansion of the universe, and how the expansion of the universe responds to the matter contained in it. Okay, and so here, the key equation was the geodesic equation, and in particular, we had the key formula that you should remember, which is that the magnitude, whether you're a massless particle or a massive particle moving through an expanding space-time, the magnitude of your spatial momentum drops proportional to 1 over a as the scale factor a expands. And for massive particles, we said that's the so-called Hubble drag that basically makes your velocity, your speed, go down as 1 upon a. So you basically come to rest with the co-moving observers who are just sitting at fixed spatial coordinates. Yeah, and so this is you know, if you might be puzzled, you know, is it a coincidence that we and all the other galaxies in the universe appear to basically be at rest with respect to some preferred cosmic expansion frame? And this says, you know, no, you shouldn't be too puzzled about that. That's the natural outcome of a lot of expansion. And for massless particles, we said that this translates into the idea that the energy, or quantum mechanically the frequency of a particle, like a photon, a massless particle like a photon, also drops as 1 upon a. And so in other words, the wavelength gets stretched exactly in proportional with the stretching of all the other length scales in the universe. Okay, and now I want to finish. There's one more thing we need to discuss about kinematics, very important thing, which is sort of the horizons in cosmological spacetimes and the extent to which they are similar to or distinct from the horizon you're probably more familiar with, which is the black hole horizon. And then we'll move on to dynamics. Again, the two key equations that you should sort of, you know, if you don't discover the equation, it's usually not cool to have it carved on your gravestone, but that's you know, you want it carved in your memory at least. The Friedmann equation. And the continuity equation. So these are the guys that we'll discuss in a moment. We're going to basically discuss the solutions of these equations and their qualitative properties. And then on the homework, you'll have a little more opportunity to derive them. You're always, of course, welcome to in the notes that lays out the steps to, if you want to go through and derive these two equations for yourself from the Einstein equations, from the metric. It's really not a bad exercise, but it's sufficiently bad that when I put it on the homework problem last year and the year before, in the feedback at the end of the class, everyone complained about it. So I've cut it off. I've responded to feedback. I'm trying to be a responsive teacher. Anyway, okay. So let's get to it. Horizons. So again, here's the version of the universe that I can draw most easily. The version where spatial sections are a spatially closed three-dimensional sphere. I'm just drawing a two-sphere on the board because that is all I'm capable of. And these are the 3 dimensions of the embedding space. Well, really, these are supposed to be the 4 dimensions of the embedding space. Okay, so let's say you're an observer here. Now, so the notion of a horizon in cosmology arises. Well, there's really 2 different sorts of horizons that happen in cosmology. So one is that so let's say you're here at this moment t, some moment, a time t after the Big Bang. Because this time t is finite, because there's been a finite amount of time since the Big Bang, it may, depending on the expansion of the space-time, as we'll see, it may or may not be the case that you've had time to receive signals from all over the space-time. So in other words, it may be the case that since the Big Bang, a signal that was emitted here has had a chance to reach you, but a signal that was emitted here has not yet had a chance to reach you. And so there's some, in between those two, there's some horizon, which is called your past horizon. So the space-time is divided into 2 regions where beyond which you simply haven't had time to receive signals from there. And then a future horizon is the opposite situation, that if you're this observer at time t and you emit a photon, you send out a photon, you want to send a signal to an alien, a distant alien, this signal may or may not, it may be that as the universe expands and expands and expands, this signal only ever makes it this far. It just never makes it to that alien, even as time goes to infinity. Okay, so that would be called a future horizon. Okay, so when do you have those 2 situations? So let's just, for simplicity, look at the case where the scale factor a of t is a simple power law in time. So it's just going to grow proportional to t to some constant power p. So in other words, in more detail, it's some constant a naught, proportionality constant a naught. So this says at time t equals t naught, the scale factor was a naught. But at a more general time, the scale factor is given by this formula. So let's assume that a naught, t naught, and p are all positive constants. And so you see that what this describes, well, when t goes to 0, this expression goes to 0. So that's saying the spatial slice of the universe has shrunk to 0 size. So that is a singularity. Einstein's equations choke at that point. And so you have to, at least according to classical Einstein gravity, you have to only consider this space-time after that singularity or before it. So you can either consider it as t runs from minus infinity to 0, in which case it describes a universe that starts at infinite size and contracts to a big crunch at t equals 0. Or you can describe it from 0, you can follow it from 0 to infinity, in which it describes a universe that starts from a equals, the scale factor is 0, the spatial universe, this 3-sphere is shrunk to 0 size. That's the so-called Big Bang. It expands from there to infinite size. Okay, so since that's the situation we are approximately in at the moment, let's focus on that case. So to study the horizons, it turns out to be very convenient. Remember, one of the key points of the last lecture was that there were sort of 2 standard coordinates, time coordinates you could choose. There's the time coordinate t, which is the one that we've been using, or there's the one where you pull the scale factor out in front of the whole 4-dimensional metric. And that time coordinate is the so-called conformal time. And then there's 2 standard radial coordinates, the coordinate r, which is sort of the radius on the Euclidean, on the 3-dimensional slice of Euclidean embedding space, And then there's this other sort of radial coordinate chi, which is sort of the intrinsic radial coordinate on the sphere, right? This guy was r, whereas this angle was chi. Okay, so it turns out that horizons are by far easier to analyze if you work in terms of these coordinates, eta and chi. So let's just remind ourselves that ds squared in those coordinates is scale factor is out front, and then it's just d eta squared plus d chi squared plus this function s sub k of chi squared times the metric for the times the angular metric for the two-sphere. And since every point on this, since this three-sphere is maximally symmetric, every point is just as good as every other point. Let's not make our life any harder than we need to. Let's just analyze the horizons for a person who is sitting right at the origin. So when they send photons, when they receive photons or send out photons, they'll be moving radially outward or radially inward. And so we can just ignore this angular factor in the metric, and we're left with, we only have to deal with this super simple metric. Basically, it looks like the two-dimensional Minkowski metric, minus d eta squared plus d chi squared. And okay, so a photon is massless, so it moves. You hopefully remember from your GR course, massless particles move along trajectories with ds squared equal to 0. Okay, and so according to this equation, ds squared is equal to 0 means d eta squared is equal to d chi squared, or taking the square root of that, d eta is equal to plus or minus d chi. And so here the plus sign is the sign that we want to consider if we're talking about outgoing geodesics. So if you take the plus sign here, that physically corresponds to if this guy fires out a photon, as time goes forward, as d eta takes a positive increment, we want the photon to go outward. We want d chi to also make a positive increment. And for ingoing photons, we want the opposite. D eta is equal to minus d chi. Okay, so let's first talk about this guy's past horizon. So if we're considering this solution, A is just a power law in time, well, because it's going to be easier to work in terms of the eta coordinate, let's convert this to eta coordinates. So remember, the definition of eta in terms of t is that, in other words, the coordinate transformation that we had to make to pull the scale factor out into the front of the whole metric was exactly this one. And so you can see that if we integrate this up, the right side will just become eta. The left side will be dt over t to the p. So the left side will be proportional to, so after we integrate, this equation will say eta is proportional to t to the 1 minus p. So in other words, sorry, I forgot my constants here. So in other words, if we rewrite this in terms of eta, well, let me just go through. So if eta is proportional to t to the 1 minus p, that says t is proportional to eta to the 1 over 1 minus p. And now if a is proportional to t to the p, it means it's proportional to this thing to the p. So in other words, it's proportional to eta to the p over 1 minus p. Okay, so let's go back to this guy. If you look at the rate of expansion of the universe here, it's positive. Okay, so a dot for this guy, as long as p and t naught and a naught are all greater than 0, a dot, the first derivative of a, is greater than 0. but now if we take the second derivative, the acceleration of the universe, a double dot, that's going to be proportional to p times p minus 1. And so that is going to be positive when p is greater than 1 and negative when p is between 0 and 1. Right? Okay, so there are these two different cases. When p is sufficiently large, this metric is accelerating. The universe's expansion is accelerating. When p is not that large, when p is less than 1, it's decelerating. And you see that here, that corresponds, that the denominator exactly goes through 0 at that transition. And so the decelerating case corresponds exactly to the case where this exponent is positive, and the accelerating case corresponds to the case where the exponent is negative. So, if you think about it, so we're trying to consider these metrics. We wanted to consider the case where t ran from 0 to infinity, where the metric expanded from the Big Bang out to infinite size. And so in this case, in the decelerating case, that if you want, since this exponent is positive, if you want this scale factor to expand from the Big Bang to infinite size, eta should also be positive. Eta should also run from 0 up to infinity. But in the other case, you have to make the opposite choice. So in this other case where p is greater than 1 and the universe is accelerating, then, since this exponent is negative, if you want this, if you took eta from 0 to infinity, that would be a collapsing universe. That's not what we want to describe. So we have to take eta running from minus infinity to 0 to describe the same expanding universe that we were previously describing in these coordinates. Okay, and that's just the same thing you would find from this, from doing this coordinate transformation. Okay, so now let's again. So now let's take our cosmologist sitting here at chi equals 0 and sometime eta. And in the decelerating case, follow a photon back in time. So in the first decelerating case, let's follow a photon back in time, and see how far away it was. See how far away it could have gotten as we followed it back in time. So we said that since that's a photon, so how much am I? Have I completely lost everybody, or am I completely going too slow? Have I managed to say all my signs backwards? Something I normally do? Not confused? I didn't just say expanding every time I meant contracting and ingoing every time I meant outgoing? Are we having honesty here? Would you guys tell me if I'm not sure we're getting a lot of honest feedback. We can't, in these sessions, we can't make progress unless we have honest communication between us. Okay, so we're talking about a photon that left at the Big Bang, traveled toward this guy. Now we're following it back in time and asking, did it start infinitely far away? Did it manage to wrap around this sphere an infinite number of times since the Big Bang before reaching this guy, or did it only travel a finite distance? Okay, so again, the geodesic equation for the incoming photon is d eta is equal to minus d chi, and so at some particular moment, if we just integrate that, this says at an earlier time. So this says if right now, if this moment now is the time eta, and we're located at position chi equals 0, let's say. So let's set chi to 0 here. And now we ask at what radius chi was the photon at an earlier time eta star. It's given by this. And so now let's just take eta star all the way back to the Big Bang. And well, you can see what happens here, that if the universe was decelerating, eta at the Big Bang was 0. It was a finite value. So we plug in a finite value here. And so this says that we start at some finite time now. We look back to the Big Bang, which was also at some finite time eta. And during that time, chi at the Big Bang was also a finite distance away. Okay, so there's some finite chi here. And if a photon left from this point at the Big Bang, it would just be reaching me now at time eta. If it left from any further away, it wouldn't have made it to me. Okay, so an accelerating, so a decelerating universe. In a decelerating universe, precisely because eta only runs to a finite time in the past, a decelerating universe has a past horizon. Meanwhile, if we took the accelerating universe, then we would have plugged in eta Big Bang is equal to minus infinity there. And so this would be chi Big Bang would be plus infinity. That would say that the photon had managed to travel an infinite distance, an infinite co-moving distance, since the Big Bang before reaching me at time eta. And so an accelerating universe has no past horizon. Okay? Now, if we just do the future case, you see it's going to be just the opposite. Okay, so we'll just flip this sign. We'll flip that sign. And now we just change the interpretation here. We say, okay, if we emitted a photon at time eta, and we want to know where it is at time eta star, what value of chi is it at time eta star? Now, if we follow this future-going photon to future infinity, to the end of the universe, well, in the decelerating case, we plug in infinity here. And so that says in a decelerating universe, if I send out a photon at any given time, it will make it to infinite chi if I wait long enough. It'll manage to traverse the whole universe. There's no spatial point that's beyond my access. Yeah.
So a few years ago, we discovered that the universe is actually accelerating.
That's true.
So in this model we got here, that shows that there should be no past horizon. In which case,
so the thing we have strictly discovered. So there's two. Yeah, go.
Well,
go.
I mean,
Sorry,
my question was then, why do we have a horizon problem?
Yeah, good question. Let me just finish this, and then that's exactly what I'm going to talk about next. So let me just, sorry. So the bottom line, sorry, just to finish the thought here, is that in a decelerating universe, there is no future horizon. You can send a photon to anywhere. But in an accelerating universe, there is a future horizon. There's some regions in the universe where if you emit a photon now, there are some distant aliens who just will never have any hope of getting that photon if the universe keeps accelerating. Okay, so now Kieran's question. Okay, so what did people think circa 1980? Circa 1980, it looked like the standard model of the Big Bang, as recorded. There's this classic, sort of semi-popular book by Steven Weinberg called The First 3 Minutes from the late 70s, which sort of describes. Oh, that's a great book. You should read it actually. But it's very out of date, but it's great anyway. But so back then, what they thought was that the universe contained basically two components: a matter component and a radiation component, and that was it. And as we'll see in a moment, that would predict that the universe was always decelerating since the Big Bang. So back in the late 70s, it was thought that the universe had always been decelerating because that's what would be predicted by all the matter that we knew at the time. And so they thought that there was a past horizon. And so, in answer to your question, Kieran, at the time it was thought that as you go to the past, there was a past horizon. So that was the source of the horizon problem. And now it turns out that the acceleration that we observe today, that acceleration is just beginning now, and it affects the future. It affects the question of whether there's a future horizon or not. Turns out the acceleration we expect today would not affect the question of whether we had a past horizon. The acceleration today would not solve the horizon problem in the past. See, I've oversimplified things by looking at a universe that was always accelerating or always decelerating. But if you have a universe that transitions, let's say, as our universe apparently does, from deceleration to acceleration, the fact that it's accelerating affects the question of the fact that it's accelerating to the future affects the question of whether there is or is not a future horizon. The fact that it's decelerating to the past affects the question of whether there was or was not a past horizon. But yeah, so there was this horizon problem in particular. Basically, so now if we are here, well, let's see how to say this exactly. So here's the kind of picture that Kendrick showed in his talk yesterday. That in a decelerating universe, you look out at the. Okay, I don't want to do it this way. Well, okay, in a decelerating universe, so here's the Earth. You're here, and here is the sphere that represents the portion of the universe that you can observe. And you look at any two points on this sphere, on the sky, and you see that they're at virtually identical temperature to a part in 100,000. And the question is why? Because now, if there was, imagine now there was a little primordial being over here who emitted these photons to you, and you asked so this is what our past horizon today looks like, but what did his past horizon look like? Well, it was smaller. It was about that big. So that's the region from which he had time to receive photons since the Big Bang, and then this guy over here, also had only received photons from this limited region, and in particular, these regions are disconnected from one another. And so the question is, how did these two, the traditional horizon problem is the question, what physical principle or mechanism was responsible for somehow coordinating the physics over here to be the same as the physics over here to within 1 part in 100,000 if they hadn't had time to interact with one another, those two regions, since the Big Bang. So another way to say that is that if we just make a plot here, in the language we were just using, if we make a plot of space-time plot of chi in this direction and eta on this axis, then if this is us today, so that's eta today, and now we follow our past light cone back, if the universe was really so we follow our past light cone all the way back to the time at which the cosmic microwave background photons were released. Okay, we haven't discussed yet the cosmic microwave background, but there was some moment early in the universe, a few 100,000 years after the Big Bang, when it suddenly became transparent, and all of these photons began flying through the universe, and we can see them today. And again, it's these guys where if we look in one direction on our light cone versus the opposite direction, the photons from those two directions have exactly the same spectrum. But now if you look at the past light cone of these guys, then if the universe, so from here to here, going this far back, we really do know that matter and radiation is all there was, or dominated the universe. So the universe was decelerating this whole time, except for the very recent epoch where dark energy began to dominate. But during this whole period, it was just decelerating. If it continued decelerating all the way back, as kind of the normal matter in the standard model would predict it would, then this guy's past light cone and this guy's past light cone on this sort of conformal diagram don't come close to each other. So that's the puzzle stated in those variables. Yeah, and then similarly, so around 1980, the inflation was proposed as a solution to several conundra like that, but this being one of them. And the way it solves that is by tacking on an early period of accelerated expansion, which, well, if this radiation-dominated era was preceded by an arbitrary amount of expansion, we see from here that would push the bottom of the diagram off to eta equals minus infinity. The Big Bang wouldn't be here. It would now be pushed down to eta equals minus infinity, in which case these guys' light cones would have plenty of time to interact with one another. And indeed, as we go back to t equals minus infinity, the two light cones will basically become nearly entirely overlapping with one another, and it will seem like less of a puzzle that they behave the same way if we look at the tip of either of those light cones. Okay. Yeah, and similarly, so again, back to what Kieran was saying, the recently discovered expansion of the universe, accelerated expansion of the universe, if as the lambda CDM model predicts, if is the sort of current standard big model of cosmology predicts, the universe now just continues accelerating forever, then again, that's a change in paradigm. It no longer is the case that we can communicate with all other observers in the universe. There's some finite region around us, and if there's no interesting people in that region, tough luck. I mean, it's a sizable region, so it depends what your standards for interesting are. And anyway, okay. So let's see. Time maybe for a joke? Okay, yes. So okay, so a man gets on a train and he sits down on the train car across from see, it hurts because I have so much goodwill right now, and then I'm going to tell this joke and it's going to be blasted for the rest of the, you're going to be like, nope. So he gets on the train, he sits down from a man in a nicely tailored suit, and the man opens up a briefcase and it's full of bananas and a salt shaker, and he opens a banana and salts it a little bit, and he throws it out the window. And he does this several more times, and the man who's just gotten on the train says, what are you doing? And the man in the suit says, I never like salty bananas. Better than expected. Better than expected. I just want to reiterate, soon you will be begging me to tell your own jokes. rather than my own. So just keep the wheels turning. They only go downhill from today's. So, okay, so our next job is to do the dynamics of FRW. So again, we have these two equations that we want to deal with. Basically, the two Einstein equations. So-called Friedmann equation and the so-called continuity equation. Okay, so first of all, let's just clean something up about this equation before we go any further. So it's conventional, you know. So this came from the Einstein equation, and the way Einstein wrote the Einstein equation, he said it was the Einstein tensor plus a cosmological constant term, lambda times the metric, is equal to 8 pi g Newton times the stress energy tensor. But we're free to pull this term over to the right-hand side of the equation. So just subtract it from both sides. And then just absorb this reinterpret this as a contribution to the stress energy tensor. And so that's what is conventionally done these days. This is called the vacuum energy. Or why is my sign backwards? What's going on here? Oh no. I'm sorry, it's right. So this minus lambda g mu nu over 8 pi g Newton is absorbed, is called the vacuum energy, and then we just write the right-hand side of this equation as 8 pi g Newton T mu nu. This is our new T mu nu, which is just the old T mu nu plus this vacuum contribution. Okay, and we'll discuss a little bit more next week why this is called the vacuum energy. But for now, let's just do that. So we're going to absorb lambda in here, and so similarly, this term will get absorbed into the stress energy tensor here. In particular, it'll be reinterpreted lambda over 3. Lambda over 8 pi g. We'll call that the vacuum energy. And absorb it into the definition of rho. So in other words, what I'm trying to say is, from now on, the Friedmann equation for us is like that. Okay, and so again, physically, this equation says that how fast the universe expands depends on how much matter there is. More matter makes it expand faster. And also what spatial curvature is present. If it's positively curved, that slows down the expansion. If it's negatively curved, that speeds up the expansion. And then this equation says, how does the matter respond to the expansion of the universe? So if the universe expands faster, if h is more positive, then because of the minus sign here, rho dot is more negative, the energy density dilutes faster. Okay, so the next thing to say is that there's an important quantity called the critical density at any given moment in the expansion of the universe. So if k was equal to 0 here, then rho would be equal to the so-called critical density. So in other words, the critical density is defined to be 3h squared over 8 pi g Newton. And so in other words, if you measure, let's say you measure how fast the universe is expanding. You measure h. You plug it into this formula, 3h squared over 8 pi g Newton, and you get some energy density. Now you look out into the universe and you measure how much actual energy density is out there. If it is equal to this critical density that you just calculated, that's telling you that the universe is flat, that k is equal to 0. Okay? If instead you go out and measure, so if the actual energy density that you measure around you is so if the energy density is equal to rho crit, we said that's the situation when k is equal to 0, and you say that's you live in a flat universe. If you go out and measure rho and it's greater than the critical density that you measured from the expansion rate, then you see from this equation k, to satisfy this equation, k would have to be plus 1. So you live in a universe with k equals plus 1. That's a closed universe. In other words, spatially it's a 3-sphere. And finally, if rho is less than rho critical, k is equal to minus 1, and the universe is open. And now k is just a constant. So if at some moment in the expansion of the universe, rho is greater than rho critical, you live in a closed universe. Rho will remain, according to this equation, greater than rho critical for all subsequent time. Or if rho is less than rho critical, you live in an open universe, and it will remain open for the rest of time, because it's not really, ultimately, it's expressing a thing about the topology of the universe, not about the dynamics. And now, strictly speaking, this is really true only about if the universe is totally homogeneous. Life, you may, I don't know, someone may be getting the idea in their head that locally it could appear to observers, if they look at just the patch of the universe that they could see, at one time it might look open, and then at a later time it might look closed, or vice versa. And that, if you live in an inhomogeneous universe, is actually perfectly true. But anyway, so far, but in terms of these FRW metrics, this is the story. And now, as I think I've said before, and as Kendrick mentioned yesterday in his talk, the observational fact of the matter is that when we measure the expansion history of our universe and get a measurement for h, calculate the critical density, and then we go out and by various other measurements measure the actual physical density, rho, it is an observed fact that they agree to within error bars. So rho, the measured value of rho today, the total energy density in our universe, is equal to rho critical, and the error bar is, at this point, roughly 1%. And again, that's another classical puzzle about cosmology. Why is that true? And again, that's another, as we'll discuss later, that's another puzzle that inflation was originally invented to solve. Although there may be other, it may or may not actually be the reason that is what it is. Let's see. Okay, so I think in terms of general qualitative terms, that's all I wanted to say. Now let's go ahead and try to solve these two equations. So here we really have two equations for three unknowns. One of the unknown functions is a of t that we're trying to solve for. Another one is rho of t, and another one is p of t. So far we have two equations for three functions. We don't have enough equations to close the system. So to close the system, we need another equation, the so-called equation of state, usually the third equation is the equation of state. If you know the matter in the universe, if you know what it's made of, you can figure out what is its equation of state. In other words, what is its pressure as a function of its density, and that gives you the third equation, so that you can solve. And in particular, it turns out in cosmology that for much of the time in cosmology, the universe can be thought of to a good approximation as consisting of several different components, each of which has an equation of state which is just where P is just proportional to rho, with a proportionality constant W. So this is just a constant. These guys are both functions of time. With a proportionality constant W, which confusingly is also called the equation of state, or the equation of state parameter. Okay, so let's solve this equation when P is equal to W rho. Okay, so in that situation, this equation just becomes and now remember, H is just equal to A dot over A. And if we pull rho to the other side of the equation becomes rho dot over rho. So this equation is rho dot over rho is equal to minus 3, 1 plus W, A dot over A. So great, that's an equation we can integrate. If we integrate this side, this is log rho. If we integrate this side with respect to time, this is minus 3, 1 plus W log A, plus some arbitrary constant. And if we exponentiate both sides, this says that rho is proportional to A to the minus 3, 1 plus W. Okay, so that's a useful equation. This says okay, as the universe expands, if it's full of matter with equation of state W, in other words, if it's full of matter where the pressure is proportional to the energy density with proportionality constant W, how fast does the matter dilute with the expansion? It dilutes as A to the minus 3, 1 plus W. And so there are three particularly important cases because they are the three constituents of our universe according to the current lambda CDM model. So those three constituents are radiation, and now next week we'll see. We'll derive why these values of W are what they are. But radiation has W equals 1/3, and so in other words, according to this equation, that says that as the universe expands, rho dilutes quite fast as A to the minus 4. Then there's ordinary non-relativistic matter, or dust as it's sometimes called. So that's like stuff that's moving non-relativistically and has mass, like you or me or any of in the current universe, basically any of the atoms in the periodic table, and the dark matter. All that stuff has pressure that is so tiny relative to its rest mass density. So remember, so P is equal to W rho. Let's talk about you guys. Rho for you is mc squared for you, plus your kinetic energy is negligible. You guys don't have very much kinetic energy, but your mc squared is quite large, divided by your volume of your body. That's your rho. The pressure in your body is so pathetically minuscule compared to that W for you is 0 to very many decimal places, and so it is with the rest of the non-relativistic matter in the universe. Okay, and so matter with rho is equal to, with W is equal to 0, dilutes a little bit slower, is A to the minus 3. And then finally, there is the so-called vacuum energy density, or cosmological constant. or dark energy, and it has pressure. It has negative pressure. It has positive energy density and pressure, which is exactly equal to minus its energy density. So in other words, W is equal to minus 1. If you plug that into this equation, you find that its energy density just dilutes as a to the 0, or in other words, it doesn't dilute at all. As the universe expands, vacuum energy just sits there without changing its value, which of course is what you would expect vacuum energy to do. Okay. Let me see. I guess I'm about to run out of time. Maybe one thing. Well, no, I guess I have. Yeah. So I wanted to say, physically. So we just basically derived this as a consequence of the Einstein equations. You know, the Einstein equations gave us this equation, and then we just solved that equation. But, you know, there's a more physical way to see where this is coming from. This is really just an expression of the first law of thermodynamics. So the first law of thermodynamics, like if you have a piston, and the change in its energy is equal to, you know, the amount of heat that flows into the piston. And then if the piston expands a little bit, so the volume of the piston changes by dV, well, the pressure inside the piston does a little bit of work on the outside world when it expands. So the energy of the piston itself is decreased by the amount of work it does, minus p dV. Okay, so let's imagine our universe once again, our three-sphere that's expanding with the expansion of the universe. And let's just draw a fictitious circle anywhere we want on here. You know, just enclose some volume here. So now as the universe expands, this fictitious volume, again, this is just, we've drawn with a marker on the surface of the balloon. And so now as the balloon expands with the expansion of the universe, this little volume is also going to expand. So let's just apply this equation to that. Well, the energy inside, so in other words, this is our piston, okay? So the energy inside this piston is, well, it's at any given time, it's the physical energy density, rho, times the volume at that time. So we want to take d of that. And that's going to be equal to, okay, the heat flow into or out of the piston. Well, the universe is symmetric. There's no, you know, at any given point, there's no preferred direction. You know, how would the heat know to flow in versus out of this wall? There's no preferred direction in which for a vector quantity to flow over here. So so the heat flow is going to be 0. And then minus p dV. Well, p, we said, we're working in the approximation or in the situation where p is just equal to a constant times rho. So this is minus w rho. And then dV again. Okay, so now let's just expand out this differential. It becomes rho dV by the Leibniz rule plus v d rho. So now we just reorganize this equation and put these two guys on the same side. This becomes v d rho. This term is equal to minus 1 plus w rho dV. Divide both sides by v and rho. So this is d rho over rho is equal to minus 1 plus w dV over v. And again, we integrate once to get log rho is equal to minus 1 plus w log v. Exponentiate to get rho is proportional to v to the minus 1 plus w. But then, so the volume here, well, the volume is, remember, we've defined a volume by just drawing with a marker on the surface of the balloon. So the volume only changes because A increases. And so as A increases, the diameter of this volume increases. The diameter of this sphere increases in proportion to A, so the volume of this three-dimensional ball goes proportional to A to the 3. And so if this thing goes as V to the minus 1 plus W, it goes as A to the minus 3, 1 plus W. Okay, so we've recovered. That's just a more physical way to recover this equation that we got from the Einstein equations, just so it's not mysterious what's going on there. Oh, let's see. Well, there's another. Oh, no. Leave that to later. Choices. Got to make choices. There's a lot of good stuff to say, and I am not too quick about saying it all. So, okay, yeah. Really, I just want to take the last 5 minutes to make good on the promise of, we know enough now to do a quick summary of the current standard model of cosmology. And so let's do it by making a plot here of the energy density in the universe as a function of the scale factor. And because these are going to vary both over gigantic ranges, let's make life manageable by plotting the log of rho versus the log of A. Okay, so according to the model that fits the data currently and has the so-called standard model of cosmology, which has basically, people have been trying to disprove it now for a little bit more than a decade, and it has withstood all challenges thus far. So there's 3 components, as I mentioned: radiation, matter, and vacuum energy. So at early times, the universe was dominated by radiation. And then its energy density is falling rather steeply. So the slope, the slope of this line is -4 because its rho is proportional to A to the -4. Rho radiation is proportional to A to the -4. Then there is another component, the matter component, which at early times is very subdominant. The density is much lower, but it's diluting less quickly. So eventually, it comes to overtake the radiation density, because it is only falling with slope -3. Rho matter is proportional to A to the -3. And then at later times, there is yet another component, according to this model, which at early times was, again, very subdominant. But since it's just a constant and everybody else is diluting away, it eventually comes to dominate. And that's the so-called dark energy, or rho lambda, and it is proportional to A to the 0, like we said. Okay, and so now we live at some point in this universe. It so happens that we live right here, sort of just after this transition point. So the moment when the matter density crosses over the radiation density, that moment in cosmic history is called matter-radiation equality. And this moment in cosmic history, where the dark energy crosses over to become the dominant component over the matter density, is called, matter-dark energy equality. And now we happen to live at a time where the dark energy, even though it's diluting much less quickly than the matter, at the present time its density is only bigger than the matter density by a factor of about 2.5. So we live really just after this moment of matter dark energy equality. Okay, so this is us. And then there are some other important epochs that we'll get to early next week. So shortly after the moment of matter radiation equality, there was an important event in cosmic history, which is that prior to that moment, the universe had been so hot that all of the atoms in the universe, primarily hydrogen, the electrons had been split. The hydrogen atoms had been ionized, split into their constituent protons and electrons. And then at that moment in cosmic history, things became cooled off enough that it became thermodynamically advantageous for all the electrons and protons to combine into neutral hydrogen atoms. Photons like to bump into charged particles. They're not so keen on bumping into neutral particles. And so suddenly, all the charged particles disappear. The photons are like, hey, where did all my friends go? And then they just have spent the rest of the universe wandering across the universe looking for them to no avail. And we catch a few of those lonely photons with microwave telescopes today and make this exquisite map of the early universe at this moment, okay? Right after matter-radiation equality, that's a few 100,000 years after the Big Bang. And then another, okay, I'm about to stop. Another even earlier thing that happens that's very important is the moment of Big Bang nucleosynthesis. Okay, that's a very analogous thing. Just like at some point it became thermodynamically, things cooled off enough that it became thermodynamically advantageous for electrons and protons to combine to form neutral atoms. Well, at an earlier point, when things were even hotter and denser, it became, as the universe was expanding and cooling off, it became thermodynamically advantageous for protons and neutrons to bind together to form compound nuclei, and in particular helium. And so basically, yeah, before this point, the universe was just all protons and neutrons. Suddenly, after this moment, that's when all of the light elements in the periodic table that's when most of the light elements in the periodic table that are still present in the universe today were made. That's called the moment of Big Bang nucleosynthesis. And it's important because you can predict in the Big Bang model how much hydrogen versus helium and various other light elements, deuterium and lithium, how much were produced, and you get the right answer. And so that gives a very impressive check that the Big Bang model was really, this guy gives a very impressive check that that we understand the Big Bang model, and that it really is true, even all the way back to a few 100,000 years after the Big Bang, when the universe's scale factor was less than 1,000th of what it is today. So A over A today, ACMB over A today was about 10 to the minus 3. But Big Bang nucleosynthesis, that there we're talking about when Big Bang nucleosynthesis over A today was more like 10 to the minus 9. The universe was the linear scale was a billionth of its current size, and so the universe was really dramatically more dense. And here we're talking about a few seconds after the Big Bang. So the fact that there's an observational prediction that you can actually go out and check in the universe today from applying the Big Bang model at that time is really, amazing. So anyway, yeah. So these are the two of the guys we'll hit earliest next week. Now, hypothetically, most cosmologists believe, but you shouldn't, it's science, you don't go by the majority. Most cosmologists believe, most cosmologists believe, and there is impressive, evidence, although not conclusive. I will try to, you'll judge for yourself. I'll tell you what it is. That this radiation epoch was preceded by an earlier epoch of inflation. So that's an epoch where the energy density was behaving pretty much like vacuum energy density, not diluting at all or diluting only very slowly. And during that epoch, the universe was accelerating like crazy. And then at the end of it, that energy density got converted by a process known as reheating to the radiation density and matter density, et cetera, that fill the universe thereafter. So that's the homogeneous picture of the evolution of the universe. In other words, that's the picture of the universe according to the standard cosmological model where we so far haven't said anything about perturbations, anything about, so far I haven't talked at all about the fact that things aren't exactly the same from point to point in space. If things really didn't change from point to point in space, then there would be no clusters and galaxies or you or I today, and so that would, be less interesting. And so that's another important thing. An important problem is to describe, we now have quite good measurements of what, the universe was very close to homogeneous at early times, but there was a tiny random fluctuations in the density from point to point in space right at the beginning of the radiation-dominated era. Those have been measured now very well, very accurately through observations of the cosmic microwave background. And those tiny perturbations, they don't do much. They pretty much just sit around until matter radiation equality. But after matter radiation equality, they really begin to grow in earnest in regions that were just a tiny bit more dense, get more and more and more dense relative to the cosmic mean until they collapse to form clusters and galaxies and stars. And you and I, you actually were not formed by gravitational collapse, so that is not really fair to say. So you guys didn't collapse gravitationally, but gravitational collapse played an important role in your existence. Anyway, yeah. So that's the story in short. And we'll early next week we'll discuss the BBN and the CMB, and then we want to basically get to the puzzles. Yeah.
Why do we say that the matter radiation quality is also the time where radiation is not on charges?
They're not exactly the same. So it's a bit of a cosmic coincidence that. Well, this is something we'll derive early next week. But there's the epoch of matter radiation equality, which is defined to be the moment at which the density of radiation fell below the density of non-relativistic particles in the universe. That was when the universe was about 1/3000th of its current size. Then, shortly after that, in the grand scheme of things, when the universe was about 1,000th of its current size, it became thermodynamically favorable for electrons and protons to combine into atoms. So that's this line is supposed to be slightly to the right of this x. This x is matter radiation equality. This line is that moment when the universe became transparent and the cosmic microwave background was released. Yeah.
Are there any theories to explain why we live so close to the matter-dark energy equality?
There are lots of theories. Yeah. That's an unanswered puzzle. It's not known whether that is a pure coincidence of. There's no theory so compelling that everyone is like, oh, that theory is probably right. There is a famous argument, much debated, due to Weinberg. If anyone else had made the argument, people would not be paying as much attention to it. But it happens to be that, like, for several decades, one of the most sensible people in the world is this guy, Steven Weinberg. And he, back in the 80s, basically made this, he was saying, what, there was a puzzle already back then. Why is the vacuum energy so small? Because according to quantum field theory, this value should be 10 to the 120 orders of magnitude higher than it is. And so he was speculating about why is it so small, and he was saying, well, if it was much larger, at the time we hadn't observed anything. At the time it was believed that it was 0, or well, we hadn't observed, it was so small that we hadn't observed it yet. But he said, well, if it was much larger than the current observational upper bound on it, it would have come to dominate. Like, let's say it was up this high and began to dominate here. Well, then that wouldn't be enough period of matter domination for. So it turns out that galaxies can only grow. Structure only grows in the matter-dominated epoch here. So the primordial perturbations don't really begin growing until matter domination begins, and then when dark energy begins to dominate, the growth turns off. So there's this window in cosmic history when interesting things can grow and form, galaxies and you and I. And he said, well, you know, if lambda was much bigger than it is now, the first galaxies would never have had a chance to form. No humans would have ever, formed in them, and we wouldn't be pondering the question. And so he said there was this anthropic explanation for why lambda had to be about this small. And then he said, well, if that's the real explanation, then it shouldn't have to be much smaller than that, because we've been able to form just fine, even if it was detected tomorrow. And then, roughly speaking, it was detected tomorrow, and everyone was like, "Wow, that argument seemed to predict the right value for the cosmological constant." But then everyone else was like, "No, that's stupid." Anyway, and so that's currently, there's still two camps who both think those two things.